Alrighty, welcome back to 353. So today we get to talk about virtual machines. How many of you have used a virtual machine? All your hands should be up because you've all been doing it. Even if you don't know, you've been using Docker, right? Been using the dev containers. You've been using, unless your operating system is Linux, you are using a virtual machine, whether you know it or not, if you're using Docker. So today we can briefly talk about them. So virtual machines. Also, plug, the ECE Design Fair starts tonight. I have 3 groups tonight, so if you want to see what some projects can be, you can go there. Lots of fun. All right, back to virtual machines. So virtual machines, like processes abstract running a program, virtual machines abstract an entire machine. So instead of running multiple programs on the same computer, our goal here is to run multiple operating systems on the single physical machine. And because they're virtual machines, of course, each operating system believes they are the only one running. They cannot see anything else. They believe they have sole access to all the memory, all the hardware, and everything like that. So some definitions. When you're using virtual machines, the host is the thing that has direct control over the hardware. So that is what, the core part is installed on. So in terms of virtual machines, there is something called a hypervisor or virtual machine manager, and that controls the virtual machine. So it controls creating them, managing them, and isolating them. So which hardware it is actually allowed to access, which physical hardware it's allowed to access. You can restrict it if you so choose. So there are 2 types of hypervisors, a type 1 and a type 2. A type 1 is called a bare metal hypervisor, so it runs directly on the host hardware, and it requires special hardware support. So that is generally the faster one for reasons we will get into in a bit. And if you are running macOS or Windows or something like that, well, your operating system is actually acting as a hypervisor as well. There is a type 2 called a hosted hypervisor that just simulates a hypervisor and runs as a normal application. So it's running a whole different operating system in user mode. So there's some tricks we have to do that, which is going to be slower. We'll get into why, but it doesn't require any special hardware, although most things now have hardware support for it. And then a guest is what we call the virtual machine, and it sees its own virtual copy of the host, so it might not see all of the hardware. So we can compare that to processes. So our diagram for processes, the world we know is on the left. So we have hardware at the lowest level, then we have our kernel running in kernel mode. We have this programming interface between, well, user mode, which is for processes, and kernel mode. Quick review, what is this programming interface called between kernel mode and user mode? Yeah, it's a system call interface. So we can look at that using strace, all that fun stuff. So this is the world as we know it. If we add on virtual machines, we just add another layer on top of that. So we take what we did before, but instead of real hardware, it's virtualized hardware. So in this example on the right, there are 3 operating systems all running different processes, all running different kernels. So one could be Linux, one could be Mac, one could be Windows or Linux. And then they are 3 different virtual machines, so they have their own set of virtual hardware, and they're all being managed by the hypervisor or virtual machine manager, which is what is actually controlling all of the hardware. So it should be noted that virtual machines are not emulation. So emulation is typically used to translate one ISA or instruction set architecture to another. So like x86 64-bit to ARM or RISC-V or the other way around. On newer Macs with the M series CPUs, it actually translates x86 to ARM very, very quickly. So you can actually virtualize a normal Windows on your Mac, no problem. So our guest operating system usually executes instructions directly on the CPU, the hardware CPU, using the same instruction set architecture. Otherwise, it has to translate the instructions from one instruction set architecture to the other, which is typically slow. It's okay for most uses, such as writing, the old 80s NES Nintendo Entertainment System emulator. So when I was in grad school, I didn't want to write my thesis, so I made one of those because, I don't know, I procrastinated and I wanted to do anything except write my dissertation. So I did that and still graduated somehow. So a virtual machine, it could use emulation to run a virtual machine on a different ISA, but generally, unless you have special things like Macs do, performance would be really, really bad. So cool things virtual machines enable us to do are pause and play. So much like our kernel can pause a process, a hypervisor can pause an entire operating system. So the hypervisor needs to context switch instead of between cores or something like that. It's context switching between virtual machines. So it does the exact same thing. It's a bit more state, but it just does the same thing as context switching processes. Saves the state, restores it. That's it. It's just we have a bit more state because we need to keep track of, special system registers and things like that. And you can also move it around exactly like a process. So this is what your server is running on, right? It doesn't go down unless my internet goes down for some reason. Because even if I need to reboot a machine, I can just migrate everything's running on a virtual machine. I can just migrate it to a different physical machine, reboot the physical machine, and then move it back after it comes back up again. So you can do that. It is great. All the cloud providers and everything will use virtual machines for literally everything. Another thing they can do, they can provide some protection through isolation. So the guests, like processes are isolated each other, guests are isolated from each other and the host. So the hypervisor can do special things like set limits on how much CPU time they have, how much memory they can use, how much network bandwidth they get, etc. And if a guest gets compromised, it only has access to its own virtualized hardware, so you just roll it back, do something like that, restore it, and then you're good to go again. So you can easily roll it back or remove it. Also good for testing malware and stuff like that, or just seeing different operating systems across the world. So anyone know what North Korea's operating system is called? It is called Red Star OS. If you would like to try it, you can download it. Highly suggest you don't actually install it on your computer, but if you want, you can install it on a virtual machine. Highly recommended you do not give that virtual machine any network access, but you can install it on there. It's isolated, you can play with it, you can do whatever you want. It's fine, no harm, no foul. Again, don't give it network access. You can create a virtual machine. Again, don't give it network access. Download as much malware as you can and just see who comes out on top at the end if you want to just have a battle royal or something like that, or do security research or something like that. But security research is generally just screwing around with stuff and trying to break stuff. So other things virtual machines help is with consolidation, like I alluded to with the cloud servers. So in data centers, lots and lots and lots of servers running, not making use of all the resources. So servers with different purposes could actually be sharing the same hardware. For instance, you could have a virtual machine for a database and a separate one for the web server and things like that. And if it's not being used very heavily, you can put both virtual machines on the same physical machine, save costs, and then once your site blows up or has more users, just buy another physical machine and you can migrate the virtual machine to a separate physical machine, and boom, you have more performance. Or you can consolidate them if they're not being used, just consolidate them all on the same machine, and if someone starts using it, then migrate it off it. So that's what's happening all the time. If you're using AWS or any other cloud provider, they're all using virtual machines, and without you knowing, your connection might be your virtual machine might be swapping between different physical machines all without you knowing. It is pretty much imperceptible when it actually switches. There's like a slight millisecond blip, but you probably will not notice it. So this is really helpful. So instead of having lightly used physical systems, make some virtual machines, run as many of them on a single machine as possible, and then, well, I don't have to bother paying for a whole bunch of different things, and I get the whole advantages of having everything completely separated and isolated from each other as well. So the key abstraction for this is something called the virtual CPU or vCPU. So for a process, part of the process control block kind of acted as a virtual CPU, but it only saved the registers that were accessible in user mode. The virtual CPU actually represents the entire CPU. So it would include a copy, its own virtual copy of like kernel-only registers. So again, processes just have enough space for user mode. A virtual CPU for operating system virtualizes all of it, including kernel-only registers. So that's the structure that stores the entire state of the CPU, and the hypervisor saves this when the guest is not running. And when the virtual machine resumes, like a process control block, it just loads the data, restores from that, and just resumes where it left off. So same idea as we had for processes. Nothing is really that new. So the guest, important to know here that from the guest point of view, or the virtual machine itself, it is still uses user and kernel mode. So there's no changes to the guest operating system. The Linux kernel or any other kernel you install on an operating system still uses privileged instructions that are only accessible in user mode. And way back at the beginning, we looked at the x86 user mode in ring 3, and kernel mode is ring 0. So you can tell how old this ISA is because, well, they couldn't rename the numbers or renumber them, and a hypervisor needs to be more privileged than kernel mode. So they renamed it, or they just named it ring -1. So if there's already a 0 and it's more privileged, well, you have to go into the negative. So on x86, it's called ring -1, and that lets it control the guest and have control over kernel mode as well. On newer architectures, it's just called hypervisor mode on ARM or RISC-V, but on older things, it's ring -1. So for type 2 hypervisors, the host basically has to create a virtual kernel mode and user mode, but user mode is kind of already done through processes. So it has to create its own kind of kernel mode because for type 2, the hypervisor runs completely in user space. So it has to kind of simulate the kernel mode in some way that we will get into. So if I am actually using a type 2 hypervisor where the guest runs only in user mode, well, if you tried to do it in your process, you just put in some inline assembly or whatever that tried to use some kernel mode only instruction, well, you would get an illegal instruction exception. You'd probably generate a trap. You'd get a wrong mode. Your program would actually crash. Well, if you're the hypervisor, you need to explicitly handle this error. So like with seg faults and everything like that, you can intercept the signal and actually do something. So they would have to actually intercept the illegal instruction signal and try to emulate or simulate what this kernel mode only operation is and just resume it. This will definitely slow it down over just native execution if it was actually running in kernel mode. So that is why type 2 is a lot slower. So how that works is this is all running in user mode. So the hypervisor or virtual machine manager, which is at the bottom of this line here, that would also be written in user mode, just written as a program. But it's something that's transparent that the guest operating system should not see. So above this line is the guest that has kernel mode and user mode. So how it has to work is if it tries to execute a privileged instruction, so it tries to execute some kernel mode only instruction, it will generate a trap, and then when that trap gets generated, the software hypervisor needs to catch it, emulate what's supposed to happen, update that virtual CPU that will have to model the actual CPU that it's running on. So that's where you would have your own copy of all of the registers that are only available in kernel mode, again, only in software. And then you return, you just resume execution of wherever the guest operating system left off, and you just do that over and over and over again. So sometimes this does not always work, because on some CPUs, especially older ones, there was no such thing as a hypervisor mode, so they did a bunch of tricks to save on instruction space and all of that stuff. So some CPUs, there's not really a clear distinction between privileged and non-privileged instructions. So some instructions are the same opcode, are the same machine code, that just happen to behave differently depending on what CPU mode you're in, because hey, that saved them an opcode back in the day. So especially on x86, virtual machines did not exist in the 1970s when this instruction set architecture came to be, so it wasn't really a design consideration. So one example is this pop-F assembly instruction on x86. It pops the flags register from the stack, and it's like, okay, well, what flags register? So the what flags register depends on what CPU mode you're in. So if you're in kernel mode, it's the kernel flags register. If you're in user mode, there's the user flags. It's the user flags. There's no way to access the user flags if you're running in kernel mode easily. So in this case, we would have a bit of mismatch. If the guest operating system thinks it's in kernel mode and executes a pop-F instruction, it should get the kernel flags. But since it's really only running in user mode, it would get the user flags, which would be definitely wrong. So we can't trap and emulate or anything like that, because this is an illegal instruction. It will just behave differently than we actually expect. So we call these special instructions, and we need another approach for them. So these special instructions need something called binary translation. So if the guest virtual CPU is in user mode, so one of the states it would have is what mode the CPU is supposed to be in. If it's in user mode and the guest operating system also thinks it's in user mode, we don't have to do anything. We can just run instructions natively as before. And the only difference is that if the virtual CPU thinks it's in kernel mode, the hypervisor has to inspect every instruction before execution, because it has to check if it's one of these special instructions. So it has to look at it before it executes. So these special instructions need to be translated to instructions with the same effect, so it's the same simulating idea. If it's just a regular instruction, we can just let it run, but we have to inspect it to make sure it is not a special instruction. And the reason we can do this is because, well, thankfully, the CPU instruction to switch from user mode to kernel mode is something we can actually keep track of, because, well, that's a special instruction, so the hypervisor can handle that using trap and emulate. So it can actually detect what mode the guest operating system thinks it is in, because, well, if we try and do that instruction, we can handle that illegal instruction, update our virtual CPU to say, hey, we are now in kernel mode, so we have to start inspecting everything. So overall, the performance is going to really, really suffer. They're adequate. Typically now, the only time you will run a type 2 hypervisor is by accident, where you forgot to enable some setting on your computer or something like that, and it's just painfully slow, and you just go ahead and try and enable the hardware support. This is also the same technique some fun tools do, so everyone's probably used Valgrind, I hope. So Valgrind does the exact same thing. That's why you don't need to recompile your program with it or anything. So it will inspect all the instructions, all the memory read and write instructions, also intercept any calls to malloc, so it can do its own keeping track of stuff. And it will do that using binary translation, which is why your program runs 70 times slower or something like that with Valgrind, but typically you don't really care, right? You're just using it for debugging. It doesn't really matter to you. So, binary translation. Visually, again, same idea. Hypervisor is under the line. The guest operating system is above the line, where there's user mode and kernel mode. But the whole thing's actually running in user mode. So if the hypervisor thinks it's in kernel mode, it's going to read all the instructions. If it's a special instruction, same idea. It's just going to simulate what happens to it, update that virtual CPU, and just continue on execution, skip over that instruction that got handled explicitly. All right, so there's also more hardware to the rescue. So this is going on what a type 1 hypervisor is. So this is they first kind of came to being in 2005, which is younger than you? Yeah, I'm not that old yet, hell yeah. All right, so after you were born, in 2005, Intel actually introduced virtualization as something called VT-X, and AMD did it in 2006 as AMD-V. There's a whole bunch of different names for these. So if you go into the settings of your computer, they might be called different things in your BIOS, depending on what the manufacturer decided. So that might also be called, when they developed it, Intel codenamed it Vanderpooled, and then published it as virtual machine extensions, VMX. AMD codenamed it Pacifica and published it as Secure Virtual Machine, or SVM. So they all mean the exact same thing. They're just different names for the exact same thing. So all this did is add that concept of ring -1 or hypervisor mode. So on your physical laptop, the host kernel, so Mac or Windows or whatever you happen to have, claims this hypervisor mode, and it's the only one able to access it. So that is how it can run your virtual machines nice and fast. So it sets isolation for the guests and what hardware it can actually have access to when it virtualizes it. So as you might imagine, there's scheduling, just like you schedule a process that we all know and love, you can schedule virtual machines as well. So if there's only one CPU on a physical machine, again, the guest doesn't know it. It could present as however many CPUs you want. The host could still present 10, 20, 60 CPU cores to the guest. They don't actually have to exist. So in this case, you would have to map virtual CPUs to physical CPUs or just schedule them like processes. So like a normal kernel, there's also hypervisor threads that keep control of the actual hardware that would interrupt them, take them off if they are running, or monitor all of the limits. So like with scheduling, one approach is CPU assignment. So if there's more physical cores than on the host than all the virtual machines or all the vCPUs across the virtual machines, you can just map them one to one. The host can continue using any spare cores, and it can be configured just to not touch the other ones. If you have to share, things get more complicated. Often this is called overcommitting. So at equal numbers, you can still map one to one. The hypervisor doesn't really run that often. And otherwise, you have to use a scheduling algorithm like we use for processes. Just nothing is really different, except that the context switch has a bit more information, but we don't really care about that. So some additional problems it might cause if we have some overcommitment issue is, while your guest operating system now runs too unpredictably for soft real-time tasks, because it might be context switched out when the user process says not to. So we know on Linux, you can just set your process to like real-time scheduling that will have priority above literally anything else. So you're guaranteed it will not be switched out. Well, if it's running a virtual machine, you ultimately do not have control over the hardware. So your virtual machine might get context swapped out, and therefore your process will get context switched out, even though you said for it not to be. So again, as a concrete example, if your process is doing real-time round robin with a time slice of 10 milliseconds on real hardware, it would kick out or context switch at most every 10 milliseconds, but the guest will not have a consistent time slice of 10 milliseconds. It might be higher if it gets context switched out between or while it's in the middle of a time slice. So this might make processes miss deadlines they otherwise wouldn't have if they were actually running on the physical hardware. So this is the only weird special case where virtualization has a different observable behavior, and this is only really for performance-sensitive tasks. For running your test cases or your labs or whatever, it doesn't really matter too much. So the only thing that gets more complicated is virtualized memory management. So our favorite topic, virtual memory. It allows each process to think it has the entire address space. Well, now the guest kernel thinks it's managing the entire physical address space, but that's virtualized. Right? Because if you are the hypervisor, you are the only one with access to physical memory, and what your operating system sees is actually virtual memory, because it's not accessing the real one. So what your process sees is actually virtual memory. Isn't that fun? So the guests, again, we have to virtualize that too. So it makes virtual memory management a lot more complicated. But thankfully, that's mostly what hypervisor mode aims to speed up, because this problem gets even worse if memory is overcommitted as well, and then we have to deal with swapping and all of that stuff. So with just relating to page tables, well, we have to do something like we have to have nested page tables. So for virtual machines, you have nested page tables to enable virtual memory for guest kernels. So again, the guest thinks it controls the entire physical memory. It does its own page table management. Again, remember the kernel running on the virtual machine is completely unmodified. And the hypervisor, that's maintaining the nested page tables that retranslate the physical addresses the guest thinks it's using to the real physical addresses on the machine. So there's a nested page table, and you could imagine, if we have a 3-level page table, on the first access, we have to go ahead, take that virtual address, translate it to a virtual address, going through 3 levels of page tables. Then we have to do it again for that virtual address to a physical address to go through another 3 levels of page tables. So that is basically what the hardware support of hypervisor mode does. It basically tells the MMU there are nested page tables here. So actually cache the virtual address to a physical address. So your lookup still would be a bit slow, but what's saved in the TLB is the final translation of going through all of those nested page tables. And if we have overcommitted memory, the hypervisor can provide double paging. So the hypervisor would do its own page replacement algorithm like we saw in the last lecture. But in this case, we might want our guest to actually do its own page replacement since it probably knows its memory access patterns a bit better. That is a bit of a less important point. So we could also use other advantages we knew from before. We can use copy on write. So guests can actually share pages if they're duplicates. So if we have 2 virtual machines running the exact same kernel, possibly running the exact same processes, well, ideally, if they were on the same or if we were running them, on one operating system, we could use copy on write, be memory efficient, all of that stuff. And so, just like copy on write, well, we can actually save memory between virtual machines by sharing pages as well. But the only difference here is instead of sharing between processes, we're sharing between guests or operating systems. So the hypervisor, there's no fork or anything like that when you create a virtual machine. You can't fork one virtual machine from another. So the hypervisor can do duplicate detection by hashing the contents of the pages. If the 2 hashes are the same, well, that means they might be the same or may not be the same. It's not possible that they are not the same. So if the 2 hashes are the same, then it will go through, check them byte for byte. And if they're the same byte for byte, then it would share those 2 pages, just like copy on write. And it would share them until one of the guests tries to write. Again, Same idea as copy on write. All right, another fun thing you can do is you can provide virtualized I/O devices. So a hypervisor can multiplex one device to multiple virtual machines, could also emulate devices that don't physically exist. So for instance, a network card. There's one physical network card on your machine, but each virtual machine can have access to it. And another thing you could do is a hypervisor could also map one physical device to a virtual device on one VM. So one virtual machine has exclusive access to the device, but the hypervisor is still in the middle, still translating because it could actually share it between different operating systems. So there's actually a newer hardware solution to remove the hypervisor during runtime, and it's called IOMMU. So this will let the hypervisor map devices in virtual memory exclusively to the guest. So now the virtual machine really does have exclusive control over some hardware, and that allows complicated things like GPU to work at native speeds in a virtual machine. So you just plug in another GPU on your machine, create a virtual machine, and just pass the virtual or the GPU directly to the virtual machine, and then it will get pretty much exact native performance. Or if there's any weird hardware things that, for instance, only work on Windows, you can do that and use Windows as pretty much native performance. So how virtual machines work is, well, just like your operating system boots from a hard drive. So if you really wanted to, you could take your hard drive out, put it in a different computer, and boot your operating system on a different machine. Virtual machines act the same way. All you really need is a virtualized disk. So you create a disk image that has all the contents of the physical disk. It would contain like partitions. Each partition would have a file system, which you are now exploring in Lab 6. Usually it's just one big file, but some formats let you split it up. And the guest kernel sees this as a normal disk it has full control over. That disk image is all you really need for a virtual machine. So if I wanted to let you run the web server that's grading your code, I just give you the disk image and say, go ahead, run this, boot it up, and you can go ahead and modify it as you wish. So it makes it easy to move to. If you're using VirtualBox or something like that, there's like OVA files that represent the virtual machine. Basically, they're just a disk image and a whole bunch of guest settings, like how many CPUs should there be by default, how much memory should there be, but like 99% of it is the disk image. That's the only important part. Another advantage of it is virtual machines can also be used to isolate an application. So going back to lecture 3 or 2, assume your application just uses a dynamic library. If you change the ABI, that causes your application to break. Well, or even more subtle, they don't even break the ABI, they just change the behavior slightly, which breaks your entire application. Well, for deployment in production,